2,000 meters is the altitude where German engineers built gigantic GAA asphalanges on the dry hills of the Sahara in 2016. Each structure rises more than 6 meters high to capture moisture. Why hang netting here? At first glance, it seems simple, but in reality, drops of condensed matter collect on the net. One can notice how they form a stream of cool, drinkable water. This was once considered a luxury in this desolate country. How can a simple gas mist change into real water? The process is only gaining momentum. The liquid flows ready for use. 60% is the precise portion of the population in the anti-Atlas region that survives without running water in their homes. For decades, this remote territory in southern Morocco has remained forgotten, clamped tightly between the scorching dry winds of the Sahara Desert. Rain falls on these lands only a few times within a single year, while the exhausting dry season can last for hundreds of days continuously. Groundwater lies deep or turns saline, rendering the remaining puddles full of minerals completely inedible for people. One can notice how women and children traverse rocky hills every morning to retrieve just a few buckets of liquid from the valley. But this is just the beginning of the daily struggle. The lack of water becomes a heavy burden, not only for survival, but also for the development of education, healthcare, and local agriculture. Why do thick mists from the Atlantic Ocean cover the mountains without relieving the drought? The fog often envelops the peaks for a few hours, creating a dense white veil. However, it disappears just as quickly without wetting the soil, leaving the land untouched by moisture. This climatic paradox inspired the German Water Foundation to initiate a daring technical solution in collaboration with local engineers. They launched a project called the Cloud Fisher to harvest water directly from the mist. The system absorbs moisture suspended in the air currents, condenses the vapor, and converts it into truly drinkable water. At first glance, catching fog seems like a fantasy, but in reality, it is a calculated engineering feat designed to sustain life. The invention was developed in cooperation with industrial designer Peter Trautwein in Munich. Transition to the next level of resource management involves utilizing this unseen potential. The technology successfully harvests a hidden water source floating in the air that most people would never expect to exist. 18 months is the exact duration the team spent testing before finalizing the water harvesting system. German scientists began this project by traveling to Morocco to investigate the terrain near the Atlantic Ocean. One can notice how the areas in the Atlas Mountains are frequently shrouded in thick morning mist. Why did the researchers focus on these specific slopes? At first glance, the weather appears to be standard mountain fog, but analysis showed that this mist contains a large amount of water vapor that can be converted into clean water. Field research revealed clear signs of high humidity on moss and tree trunks. But this is just the beginning of the process. The German team collaborated closely with local communities to choose the right location for the pilot project. It seems like a simple task to place collectors, but in reality, the precise site determines the efficiency of extraction. Researchers tested different types of nets to maximize water reception. The process is only gaining momentum. Ultimately, a special three-dimensional net was selected for its superior efficiency. These nets were mounted on solid steel frames. One can see how the structure forms a gigantic mist wall against the mountain sky. The Cloud Fisher system acts as a huge gas wall positioned in the air. Moisture-resistant winds from the Atlantic Ocean blow over the slopes of the anti-Atlas Mountains. Almost 1 meter of depth is required for the foundation coves dug into the hard soil of the Atlas Mountains. German engineers began with the preparation of the foundation for the mist collection system after a careful research of the terrain and wind patterns. Why did they hire local African workers for this technical task? These people were already familiar with the rough soil and the harsh climate, making their experience indispensable. They dig large coves to serve as anchor points for the steel support poles, ensuring stability against the elements. This foundation serves a critical purpose, keeping the frame stable against the strong winds blowing incessantly from the Atlantic Ocean. One can notice how the engineers and the villagers start to carry the heavy steel frames on the rough, rocky slope. They move them to the installation location, while the cold wind from the Atlantic Ocean pulls them in, adding resistance to every step. As soon as the frame is straight, the team firmly holds the steel pole in place while teammates tighten the connections. Action intensifies as they tighten the bolts with significant force to lock the structure into the massive rocks. The entire assembly is set to withstand the strong desert winds that batter these heights. But this is just the beginning. High above the ground, workers climb the ladders with safety harnesses and hang suspended to tighten each three-dimensional panel over the steel frame. Therefore, they carefully adjust each bar to form a huge mist wall over the mountaintop. The core of the system is formed by a double layer of three-dimensional mesh made of ultra-durable polyethylene. This material exists to resist ultraviolet radiation, corrosion, and the extreme temperature fluctuations between day and night. At first glance, it looks like a simple fabric, but in reality, the two layers are parallel to each other, causing millions of small openings where mist drops get stuck when they fall through. It is visible how the mesh picks up the mist, creating a need for a good channel to catch every drop. That is the moment when the water gutter is installed to capture the flow. The technician holds the V-shaped composite gutter in its place and then turns each hook and steel bolt to firmly attach it to the mesh frame. Each connection is carefully adjusted to ensure that all condensed drips flow into the gutter and subsequently into the container without losing even one drop. Finally, they secure all connection points to ensure that the gutter is firmly attached to the frame and does not slide in the hard wind. Everything only gets more complicated. Consequently, each contact point is turned back again so that the water flows straight into the container without loss. Each Cloudfisher unit is built as an independent modular structure that can be put together using only a few simple tools. No heavy machines are needed, no electricity is required, and no fuel is consumed. Only wind and gravity are needed to drive the mechanism. This simplicity is exactly what makes the Cloudfisher one of the most sustainable water supply technologies in the world. Because of this, it is perfect for aid organizations and remote areas where the drilling of wells or the building of dams is almost impossible. From a distance, the nets on white sails look like a sea of sand filled with wind, which fish out water from the air. The principle behind the Cloudfisher is simple but refined to almost perfection. When the wind is blowing over the three-dimensional panels, the small moisture droplets in the air collide against the cool mesh surface and begin to condense. Due to surface tension, they form small, shiny beads on the mesh at first. But as more droplets arise, they melt together into larger droplets, directed by gravity and the sliding frame. These droplets slowly slide down and fall into the gutter that is placed parallel to the ground. From the gutter, the water flows through a closed plastic guide system to a central storage tank, which is hundreds of meters or even kilometers away. The result is a closed, elegant, and durable cycle where mist becomes water and water becomes life. 600 to 1,000 liters of water per day are absorbed by a system containing about 10 Cloudfisher panels. Even during the hottest months when the temperature rises above 40 degrees, the collectors function efficiently. One can notice how clear drips form on the mesh, even if the air appears completely cloudless. This volume is sufficient to provide a whole village with all daily needs. The Cloudfisherman keeps getting clean water to thousands of people in the clear desert. But this is just the beginning. Why was such a system necessary for the region? Traditional extraction methods were proving unsustainable. According to the local residents, They used to spend 3 to 4 hours a day collecting only 20 to 25 liters of water. This amount was barely enough for the daily needs of a family. Now, with the Cloudfisher system, the routine has transformed. Residents just turn the tap open and have water to cook, wash, bathe, and even water plants. Something that was once unthinkable in the desert has become a reality. However, water is really not free. The German team has made a sustainable business model of it. People pay based on how much they use, costing about $1.20 to $1.50 per cubic meter. At first glance, this pricing seems restrictive, but in reality, it helps prevent waste. The more people consume, the higher the costs rise, stimulating responsible use of precious water sources in such an extremely dry environment. But for people in the lowest income groups who cannot do anything else, the struggle persists. They walk outside the remote mountainous areas of Morocco to find sources. One can see them spending hours digging out polluted water with their hands. They know it is unsafe, but still have no other option because it is the only source in the Weiden area. They carry heavy jerry cans weighing almost 20 kilograms tied to their backs. The camera glides along the path as they take slow, strenuous steps to bring the water home. Back to the Cloudfisher system, the scale of operations is massive. From spring 2016 to the end of 2018, the German team built the largest mist reception installation in the world. It gets more complex further on. The system now supplies clean water for 15 villages, 1,250 people, and a school. It also supports agriculture and 7,000 heads of cattle. 31 cloud shards have been installed, all connected by 26 kilometers of pipelines. These lines feed into 5 storage tanks with a total capacity of almost 1,000 cubic meters. On average, every square meter of the mesh collects 22 liters of water per year. In total, the 31 cloud fishermen can produce more than 36,000 liters of water per day. This calculation comes down to tens of millions of liters per year. The system consumes no energy and almost does not need any maintenance. It works in practice as a one-time investment that goes on for years. Thus, the technology remains completely environmentally friendly. 80 days per year was the duration residents of the capital had to wear protective masks in the 90s to prevent inhaling fine dust. Enormous storms originating from the Gobi and Taklamakan deserts routinely covered the air above Beijing, turning day into night with terrifying speed. Why did the sand swallow entire regions so rapidly and with such intensity? It would seem that deserts are static geological formations that should not encroach on inhabited lands. But the combination of deforestation, overgrazing, and excessive groundwater extraction destroyed the soil structure, opening the path for uncontrolled erosion across northern China. Confronted with this growing threat, the government launched an initiative on a scale of centuries in 1978. The program for the 3 northern protection forests, worldwide known as the Green Great Wall, is not a single barrier, but a vast network. It includes thousands of forest belts, windbreaks, and ecological lakes extending over 4,500 kilometers. The line stretches from the autonomous region of Xinjiang to the province of Heilongjiang, covering almost the entire north of the country. The goal is to plant 35 million hectares of new forest by the year 2050 to permanently halt the desert. Because of this colossal effort, the forest cover of the country increased from only 10% in 1949 to more than 25% today. It is considered the largest ecological project ever built by man on land, utilizing the green color of life itself instead of concrete. But this is just the beginning. Engineers did not start with heavy machinery, but with a well-calculated aerodynamic plan using satellite images and drones. At first glance, spreading straw and sand seems like a simple, primitive solution, but in reality, it is a complex technical operation designed to alter wind flow. Specialists analyze the movement of dunes to design a huge raster system of straw checkerboards. Squares measuring about 6 by 6 meters are laid out in geometric patterns over the burning dunes. One can notice how the landscape turns into a gigantic dashboard of golden squares that stretches out to the horizon. However, behind this simple image lies an expensive execution under barren circumstances. Millions of kilograms of straw are transported hundreds of kilometers to the heart of the desert, where asphalt ends and soft sand begins. Teams of workers laboriously dig deep trenches and place bundles of straw in precise lines to form the grid. Temperatures rise above 49 degrees Celsius under the merciless sun, with absolutely no shade to detect for miles. Every movement feels like a battle against heat and exhaustion, yet thousands of workers remain hard at work. It gets more complex further on. Mechanical soil drilling machines enter the grid as soon as the straw is in place. Augers drill small holes in the exact middle of each square, preparing the soil for drought-resistant species such as saxaul, desert poplar, and red willow. The seedlings are carefully tended in nurseries before they are brought to the desert for transplantation. Each young plant is positioned so that the vulnerable roots nest just below the surface, where the straw layer protects them against the burning sun and wind. One can see how workers add a measured amount of water and compact the soil around the base to ensure full contact with the moist layer below. The protective grid maintains its purpose as the weeks pass, cooling the surface and reducing evaporation. Over time, the straw gradually decays under the influence of wind, dew, and microorganisms, turning into an organic blanket rich in nutrients. This natural fertilizer feeds the developing root systems, helping them to spread deeper into the stable soil layers. Thus, what started as a few vulnerable seedlings develops into a living network that anchors the dunes and begins the long recovery of the land. Thousands of hectares require anchoring to begin the long process of recovering from the desert. Why is this stabilization critical? At first glance, the dunes look still, but in reality, wind erosion would erase any progress immediately. Mist-catching nets in Europe and forests in the deserts of Asia provide the necessary shield. But this is just the beginning. One can notice how these technologies quietly preserve the future of the world's driest countries. Each story offers a new perspective on the power of science. It is visible how the landscape transforms under this influence. The struggle for moisture reaches a steady rhythm,